Hi everyone, how you guys doing? So first of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online platform for IIT JEE. And on this channel, everything, as you know, is taught to you completely in English. So this is a series that I host for class 12 students, and the topic that we are covering right now is current electricity. And today we'll be talking about RC circuits or circuits having resistors and capacitors both. Okay, so before we get started, let me introduce myself one more time for those of you who still don't know me. Okay, so my name is Rohit Dixit. I study mechanical engineering from IIT Delhi, and for almost past 8 years, I've been teaching physics for the JEE exam. Now, all this teaching so far had been offline. So all this so far had been offline in offline setups, and offline I've been associated with some of the topmost institutes in the JEE field. Now, I myself was All India rank 447 and All India rank 192 in the two stages of the IIT JEE exam that I took. Okay, Sabrish, yeah, that happens. That happens, unfortunately. That is why we guys are there. So if you are unable to understand that, then you can follow us here. That is why Unfortunately, that is the case. That is the case. The level of teaching is not very apt in most of the places, and that is why you need to seek a good teacher. And you can keep following my lectures. I will try to help you with all the concepts and the areas where you are having problems. Okay. So as I was saying about myself, so I also qualified the NTSC Stage 2 examination, and I was also in the top 1% in the NSCP or the National Physics Olympiad exam. I've already coached many students to top ranks in the IIT exam, both mains and advanced, in the offline setup. Now I hope to continue doing that with the Unacademy Plus. And this is also how you can also make sure that your studies are not getting interrupted and you keep your edge there in this competitive, highly competitive exam. So you can get your uncapped subscriptions. The subscription will give you benefits like live classes. You will get to interact with the educators. So that completely takes care of your teaching, your studying. As far as even the lockdown period is concerned, your classes, you will have regular classes here online. And if you have any problem areas, then of course that will be taken care of, like Sabri said. Now, you also have live polls and leaderboards in these classes, which keep them highly interactive so that the learning is not only continuous but also effective. Then, of course, you have a test series and then you have analysis sessions for those. This is also very important when it comes to a competitive exam like the JEE, because self-assessment and identifying the areas of improvement is very important. And of course, you have live doubt clearing sessions. So, as I keep telling you that. For all Unacademy Plus courses, all of them have this feature that every fourth session has to be a live doubt clearing session after 3 teaching sessions. Good evening, Rishabh. How are you? Hello, Ananda. Long time. All right. So again, on top of all these benefits, Unacademy is also giving you a chance to study from the best educators in India with your subscription. So Unacademy has rounded up some of the topmost teachers in the JEE industry, and it is giving you the opportunity to study from the top teachers in the field from the safety and comfort of your home. Okay, so how do you get this subscription? It's very easy. First, you will need to install the Unacademy app. Once you've done that, go to the plus section in your app, select your goal as IIT JEE and click on get subscription. So when you're getting your subscription, you can use this code. This is my code, RD Live. You can use this code and get a 10% off on all these fees. These fees have been kept very competitive compared to what you might be paying to any of the offline institutes that you're joining. So any offline institute would charge you a fees of 4 to 8 times this. So trust me, at these prices, the kind of content and the kind of guidance that you will get here would be definitely worth it. So if you can, go ahead and get this subscription. Use this code to get 10% off in your subscription fee. If you cannot get this subscription, then also you guys can keep following us on the Telegram, on the YouTube channel of JEE English. And for that, you will need to connect with us on the Telegram app with the link above so that you're not missing out on any of the lectures or sessions happening here. So, without any delay, let's get started with today's topic of discussion, which would be RC circuits. So, in the last chapter, when we were discussing capacitors, we discussed about charging of capacitors. We connected a capacitor with a battery. Yes, Ananda. And we realized that the capacitor got charged instantaneously. Alright, instantaneously the capacitor, the potential difference across the capacitor becomes equal to the voltage of the battery. And we still saw that there was some loss of energy. Alright, whenever a capacitor was connected across a battery of volt V, we realized that almost instantaneously it acquires a potential difference of V and it stores an energy which is half CV square. Now in real life, of course, this kind of situation will never happen. Why? Because in real life situations, your wires, your connecting wires, they can never be idle. So there will be some inherent resistance, or even your batteries will have internal resistances. So in real life, whenever you are trying to charge a capacitor, you actually are dealing with RC circuits. So that is what we are going to discuss today. An RC circuit is nothing but a circuit containing both a capacitor and a resistor along with a battery. Or sometimes maybe the battery is also not there. But there has to be a resistor and a capacitor. That is the primary requirement for an RC circuit. So let's start. So as I said, in real life, all the circuits have resistances. An RC circuit is a circuit containing resistances and capacitors. Analysis of RC circuits can be done with the help of KCL and KVL. And the simplest of the RC circuit is what you see here. This is the simplest possible circuit. And as I said, all the analysis will again be done by KCL and KVL. These laws, as I keep telling you, are the fundamental laws based on fundamental principles of conservation of energy and conservation of charge. So these can be applied in any situation. Doesn't matter what kind of circuit it is, whether it is having only resistors, whether it is having only capacitors, or whether it is having both resistors and capacitors, or even other circuit elements like inductors, about which you will study later this year. So RC was again one of my weak topics. Don't worry, Rishabh. Don't worry. We will go through it, and hopefully it won't be so anymore. Okay. So first kind of circuit that we talk about is that you are trying to charge an uncharged capacitor. Yes, Ananda. Yes, absolutely correct. So that is called a charging circuit for a capacitor. So this is what a charging circuit would look like when you're trying to charge an uncharged capacitor. So there are some assumptions. So we are assuming that initially this capacitor is uncharged. Initially the capacitor is uncharged. So that is uncharged. Okay, and I'm assuming that in some time t, see the moment I switch on the circuit, some current will start following, and after time t, I'm assuming that it has picked up some positive charge here. So we are assuming that it has some positive Q charge here. Then of course it will have a negative Q charge here, and the current at this time in the circuit, let's assume, is t. So this is situation at time t. Okay, so let's just write this somewhere. This is situation at some time t. Okay, so let's write about that also. At time t, the various parameters of the circuit are as shown. Okay, so this is what we are assuming, that initially we had an uncharged capacitor and it is connected in a circuit where there is a battery and there is a resistance, and we switch on the circuit at t equals 0, and after time t we are assuming that the capacitor has acquired charges of plus q and minus q, and at that instant the circuit has a current of I flowing in it. Yes. Time t means some intermediate stage. Some time t. At some random time t, I am assuming all these things to be present in the circuit. Alright. Now what I will do is I will study the relation between these quantities. So what we do is we start by using your KVL laws. Because see, there is no need for KCL. There is a single loop only. So there are no nodes. So let's just apply KVL. Let's see what that gives us. Now, applying KVL, applying KVL in the circuit. Let's see what we are getting. So let's start our KVL loop from here. So when I am going from here, and I'm assuming I am moving like this. So when I cross the battery, I will have a potential difference of plus V. Similarly, when I am crossing a capacitor from its positive side to its negative side, the change in potential would be Q by C. Okay, and it would be negative. Okay, because I am going from higher potential to lower potential. Similarly, when I cross this, I will be crossing this in the direction of the current, right? So if I is the current, I am crossing this in the direction of the current. So I will get a potential change of minus IR. So if I write all that, let's see what we are getting. We will get that plus epsilon minus Q over C minus IR equals 0. So that is the expression that I am getting for my KVL. And I also know that, imagine if I is the current going in dt time, this current will increase this charge by small dq. So let's assume after dt time what happens. Okay, so after dt time, this current would have gotten an additional charge here, which would be dq would be I times dt. So also, if charge gained by capacitor in small time dt happens to be dq, then I can say that the dq would be nothing but I times dt. Why? I obviously is defined as the amount of current which is flowing per unit time. So in dt time, how much charge would flow? Okay, so I is the current. It is the charge that is flowing per unit time. So in dt time, the charge flown to the capacitor would be I times dt. So now I will use that. I will say also I can be written as dq over dt. So let's substitute that in our equation and let's see what we are getting. So when I put that here, I will get plus E minus Q over C equal to R times dq over dt. Okay, so I am getting a differential equation where on one side I have quantities of charge and on the other side I have dq by dt. So let's just simplify this a bit and I can write C times E minus Q over RC equals dq over dt. Now all I need to do is integrate this expression. So I will get all the q terms at one side and I will get every other thing on the other side. So let's see what we get. We will get that dq over Ce minus q equals RC dt. Now all I need to integrate this, and what I know about integration, that initially at time t equals 0, the charge on the capacitor was 0, and at time t, the charge on the capacitor is q. Okay. So when I integrate this function within these limits, let's see what I am getting. I am getting here the integral would be minus times ln of, so minus ln Ce minus q, having limits from 0 to q, and that would be equal to Rc times t. Okay. I hope everybody is following this. This is normal mathematical integration, nothing new about this. Now what I will do is, now I will write this as, which can also be written as ln of Ce minus q over Ce This is, I have put the limits equals minus RC times T. Okay. Now all I need to do is rewrite this in another way where I can say CE minus Q becomes equal to CE into e to the power of minus RC times T. Okay. Okay, yeah. I made a slight mistake. Yes, that's what I was thinking. Yeah, here there was a slight mistake. RC. RC would be over this. Yes, so I will need to write T over RC. Let's just correct that. So similarly here also it will be minus T over RC, and eventually here also that is what I will get. Minus T over RC. So from here I am getting that Q equals CE. I am taking common. If I take CE common, I am getting 1 minus e to the power of minus T over RC. So that is the expression that I got for the charge in the capacitor as a function of time. Okay, so let's take a look at that again. So the expression for charge that I am getting is Q equals CE times 1 minus e to the power of minus T over RC. So if I want to draw a plot of this, let's see what kind of plot I will get. This is the kind of plot that I will get for charge. Okay. So yeah, they have shown you the charge, the plot of potential. The potential plot would also be very similar to the charge. Why? Q equals, V equals Q by C. So Q by C here would give you the potential difference across the capacitor. So one equation is this. Similarly, I can also write V across capacitor would be Q over C, which is E times 1 minus e to the power of minus T over RC. So let's try and start taking a look at these graphs. What is this graph telling me? This graph is telling me that the charge on the capacitor, what happens if I put my T equals 0? If I put T as 0, then I'm getting charge on the capacitor as 0. So even if I draw this Q versus T graph, Q versus time graph, you will realize initially the charge would start increasing and eventually it will reach a final value of C times E. Now if you will remember, if EMF of the battery was E, then even without the resistance, the final charge would have been C times E, right? Hi Satvik. So you did not miss much, we just started with the derivation. You just missed like 2-3 minutes of the derivation. Okay, so this is how the charge on the capacitor is changing. It starts growing and then the growing is slowing down, you will realize, and eventually you will realize that the maximum charge that the capacitor can have across, when connected across a battery of EMF E, would be C times E, right? And to acquire that charge, it actually takes infinite amount of time. Okay, you will realize in this equation, you will realize that if you put T equals 0, you are getting Q as 0, and if you put T as infinity, then you are getting your Q as CE. So the charge in the capacitor will grow from 0 to CE. It will follow a path like this, and it will actually take infinite amount of time for the capacitor to get fully charged. Similarly, the voltage across the capacitor would also change from 0 to E, which is the voltage of the battery, and again it would reach there roughly in infinite time. Also, what I can do is I can start writing the equation of current across in the circuit. So I know I would have been equal to dq over dt. So if I differentiate this expression with respect to time, let's see what I'm getting. I'm getting I as epsilon by r into e to the power of minus t over rc. So you will realize that the current in the circuit will start At t equals 0, it will be epsilon by r. Okay, so this is what your current would be. And then with time, it will start reducing, and eventually at t equals infinity, it will become 0. Okay, so now from here, what can I observe? What all can I observe? So the first thing that I can observe is it takes infinite amount of time, or infinite time, for capacitor to get fully charged. So that's the first thing that I will notice. Now, second very important thing, if you notice about the circuit, is that at t equals 0, what is the current in the circuit? It is epsilon by r. Imagine if there was no capacitor, if I remove this, then what would have been the current in the circuit? It would have been E by R. So at t equals 0, what I realize is that the capacitor is not changing the current, and the current is flowing as if there was only resistance present in the circuit. So that is another important conclusion that I can see from here, that at t equals 0, this capacitor is behaving like a normal wire, as if instead of capacitor, what if I just connected these with a normal wire only, and if I did not have a capacitor, then you realize the current would have been epsilon by R. So that is another thing that I will observe from this. At t equals 0, I can say at t equals 0, the capacitor behaves as a resistanceless wire. The capacitor behaves as a resistanceless wire Okay, that is how I can see the current in the circuit flowing. Similarly, what happens at t equals infinity? At t equals infinity, the current is 0. So why would it be 0? Imagine what is happening if I had an infinite resistance here. If I had an infinite resistance over here instead of this capacitor, then of course the circuit current would have dropped down to 0. So the third thing I can notice from these expressions is that at t equals infinity, the capacitor, a fully charged capacitor, that is, will behave as an infinite resistance. So that is another thing that we will notice, and then later we will use all this information. Also at t tending to infinity, the capacitor gets fully charged and behaves as an infinite resistance. So this is very, very important, guys. As an infinite resistance, it makes the current go to 0. It shows the characteristics of an infinite resistance. Hi Vineet, how are you? Next thing, of course, is that you will also realize one important thing here, that obviously at this time the potential difference across the capacitor is same as the potential difference across the battery, or the EMF of the battery, and you will realize at t equals infinity, now nothing is changing. You realize all the circuit parameters, as I said here. What are my circuit parameters? Circuit parameters are the current in the circuit, the charge on the capacitor. So both these circuit parameters are constantly changing with time, and after t tending to infinity, all these values become constant. So you realize in this graph, everything is always changing with respect to time, but after a lot of time, let's say from here, everything almost becomes constant. Here, everything becomes constant. This is what we call steady state. Okay, so please remember this. This is what we call steady state. No, not t equals 0, t equals infinity. See, the word steady means that something does not change, that is steady. So at t equals infinity, the circuit is called to be in steady state when its parameters, circuit parameters have stopped changing. See, you should remember this. In thermodynamics also, when do you call the system to be in steady state? You remember in your heat transfer, when the heat passing through every section becomes constant, and when the temperature of every section becomes constant, and I told you that in transient state, that value keeps on changing. So whenever the values or the parameters associated with anything stop changing with respect to time, then that is called steady state. Even for flow, fluid flow, in steady state, nothing is changing with time. Your velocity can change with area of cross sections at different positions, but with respect to time, they will not change. If at any point the velocity of the fluid flow is v, then after some time t also the velocity will be t only, v only. Okay, Vineet, I hope you got that. Now this is what you are calling steady state. So I am writing that here. Okay, this is called the steady state of the circuit. See, always remember this. Whenever you see the words steady, steady means when things stop changing with time. Next chapter कौन सा है? So next chapter magnetism होगा भाई. Because I have one more lecture I think on current electricity where I will discuss measuring devices. So voltmeters, ammeters, galvanometers, and your meter bridges and yeah, those things. After that, we will start with magnetism. Okay, so I hope you got your answer, Rishabh. What steady state is. So please remember the word steady. Just remember, steady means okay. I'm glad I will see you there. Okay, so word steady means steady is used when parameters stop changing with time. Parameters stop varying with respect to time. For anything you will see. That is what you will call steady state. May you know the date. So probably next week. Next week we will start, okay? Maybe this is Saturday, right? So maybe I will take at least one more class of this current electricity, that is on Tuesday. Maybe one more if I have to, then probably on Thursday. So we will either start the magnetism chapter by next Thursday or maximum by next Saturday. Okay. One practice session. Yes, of course we will have a practice session also. Okay. So definitely then let's make it Saturday only. Okay. So please remember this. Yes, oh yes, Tuesday is the quiz, right? So Tuesday is the quiz day, of course. No, I think I will still have a session. Along with the quiz only, I will have another session of teaching also. Okay, don't worry. Because, sir, 12 सिर्फ 3 days होता है क्या? हाँ. I conduct classes of 12 for 3 days and classes of 11 for 3 days. So I conduct classes like 6 days a week. Okay. Alright, so as I said, everybody should be clear what steady state means. It doesn't matter where you see steady state, whether you see it in electrical circuits, whether you see it in fluids, whether you see it in thermodynamics. We call anything to be in steady state when the parameters linked to the state stop changing with time. Okay, so please remember this definition. Now we will talk about something interesting which we call time constant. So what happens is that you realize that the total time taken for any capacitor to get fully charged is theoretically infinite. So obviously I am not going to wait for infinity to charge my capacitors. So I will almost want to charge maybe my capacitor to 99.5% or something like that, and that's about it. Because for 100% charging, it would usually take infinite amount of time, and there is no point of charging it for infinite amount of time. So what's the point if I can't even use it? So what we do is we talk about another term called time constant. Suppose you have two RC circuits. Suppose you have two RC circuits and you wanted to compare in which one is the capacitor charging faster. So imagine you had this one circuit and then you had another circuit, and I wanted to compare that in which of the following situation is the capacitor charging faster. So then what we do is we compare their time constants. Okay. So as I was saying, what is the need for time constant? It is there because the actual time for fully getting charged is infinite. So I can't keep saying, okay, I will wait for both the capacitors C and C dash to get fully charged. Both of them will take infinite time. So that will not be a true, way to judge or compare the two circuits of, which one is getting energy faster, which one is charging faster. So what we do is we study it in terms of time constants. So as I said, since the time required to fully charge the capacitor is infinite. So instead of talking about the charge time that is required to fully charge this, we actually start talking about another time. Is infinite for comparing or studying these circuits, for comparing or studying RC circuits. We talk about something called a time constant. Now let's see what a time constant is. Now let's go back to the expression which we had of charge. So Q was CE. So since Q is CE times 1 minus e to the power minus T over RC. What you will realize is that if at t equals infinity, you will realize Q is CE. And what happens if I put the value of T as RC? And at T equals RC, you will realize Q becomes CE times 1 minus 1 over E. Okay, so this is what we started calling time constant. Hi Osho, how are you? So you will realize that this is nothing but, I can write this as capital Q. Okay, so Q is here, this which I am calling capital Q, which is the maximum possible charge in the capacitor. So this becomes capital Q times E minus 1 over E. Okay. I did take a class on Thursday also. And Tuesday I had a quiz. So for 12th I did not miss any session. No, for 12th I did not miss any session. I just took 2 days off on Wednesday. I just took 1 day off actually on Wednesday, and Monday I had some special classes planned on the app. So yes, for 2 days I was not there on YouTube. I was there on Tuesday, I was there on Thursday, I was there yesterday. Why, sir, nowadays no classes? Okay, so what? No, I just took a couple of days off to take care of certain, stuff, because you guys, I don't know if you realize this, that I take classes like 7 days a week. So I hardly get time to take care of other things. So that is why I wanted to take a couple of days in a month. At least I should get a couple of days where I can, take care of other stuff. No, there are regular classes happening now. Don't worry. I just took 2 days break. What are you saying? Okay. So, I don't know if you know about radioactivity. A similar thing happens in radioactivity also. The time taken for any radioactive element to completely disintegrate is infinity. So there also we do not talk about the time. We in fact talk about half-life. I don't know if you guys have heard it. So what we decided is that to judge the rate of disintegration, let's talk about a quantity which we can measure, which is not infinite, which is a finite quantity. So similarly for these circuits, we decided that okay, let's make life easy. Instead of comparing the times taken for completely charging the capacitors, we will take the time where the current becomes this much. And what you will realize is, what is this current? What is the value of E? It is 2.61. So it is 1.6 over 2.6. So that is roughly 60%. Roughly 62% of. So Q equals is roughly, I think it comes out to be 62.8% of capital Q. So that is how you define your time constant. Time constant is the time in which the capacitor acquires 62.8% of the total positive charge. Yes, it's roughly around that. I don't know. Let's just check the actual calculation. What we usually use 62.8% only. So, but if you want, I can calculate that exactly for you. So it will be 1 minus E, or E minus 1 over E. So yeah, that is 63.2 actually. 63.2%. 63.2% of capital Q. So that is what you call the charge, the time constant. So this time is called the time constant. And what you will realize is that after every such time, the charge would become, it would increase by 63% of the original value. Okay, so the increase in charge would be percentage wise, it would be similar. Okay. Yes. So in half-life, if you remember, in half-life what we say is that after every this time the charge becomes half. The quantity of radioactive element becomes half in all the half-life time. Similarly, in a time constant, the charge acquired becomes 60 from initial to final. In the middle, it will become 63.2% of the total maximum possible. If you talk about current also, you will realize in terms of current at T equals RC. Let's see what is the current in the circuit. Current in the circuit would become epsilon over R times 1 by E. Right, so you can see from this equation. In 2 time constants, it will become epsilon by E square. In 3 time constants, it will become epsilon over R by E cube. So in every 1 time constant, the value of current is getting reduced by a factor of E. So there it is similar to your half-life. In half-life, what is happening is, hello Naman, how are you? In half-life, if you remember, in T half, every time the quantity of the material becomes half after every half-life. After 2 half-lives, so 1 half-life, it becomes this. Similarly, 2 half-lives, it becomes a 1/4 and so on. Similarly, here what you will see is that if we call this as tau, then in 1 tau, I equals I naught over E. In 2 taus, I becomes I naught over E square and so on. So you realize what is happening in time constant. 1 time constant is that after every 1 time constant, the value of current in the circuit is dropping by a factor of E. And that is what we use. This is the value that we use for comparing different circuits and to decide for which circuit the charging is happening faster. So whichever circuit has a smaller time constant would mean that that circuit is charging the capacitor faster. And practically what we do is we consider the steady state to be after 5 time constants roughly. Okay. So you will realize, so after 1 time constant it is 63% roughly. After 2 time constants it will go more. And after almost 5 time constants, practically we assume the capacitor to be fully charged, and we assume the steady state to have arrived after practically after 5 time constants. Okay. Okay. So yes, PDFs is taking a bit of time. So actually, there was a lot of PDFs of everybody, So the team is still getting that sorted, and it will take about 1 week for the PDF to get uploaded. So that is an issue. I will try and ask them to maybe upload this particular PDF. Which PDF did you want? Did you want any one PDF in particular? Maybe I can request the team to upload that quickly. So see, somebody in the team is responsible for managing all these PDFs and managing all these links. Hi Chinmay. So what happens is that that person would manage these PDF links for every educator, not only on JEE English, on just other channels also. Okay. So there had been an issue because there was a lot of mix-up because there were so many educators and everybody is uploading their own PDFs. So we have a common place where we all upload our PDFs. So that it was getting sorted. The team was trying to get that more organized to avoid any confusion. Okay. So that is why they told me that it will take about a week's time to get it everything sorted so that they can make all the PDFs available properly, because somewhere I think there were mistakes happening in those also, and all the playlists would also get sorted because I think there was some problem with the playlists also. So the team was working on that and they said it will take about 1 week's time, which is okay. So I don't know if I can class 12th physics chapters 1 to 7. That is going to be almost impossible to be uploaded by tomorrow because I don't think I have taught so many chapters so far, have I? Okay, I may try talking to them. Okay, I will try if I can get all these PDFs uploaded. So this is what we call time constant. This is called time constant. Okay. RC is called the time constant tau. The time constant in the circuit so now there are two ways of defining this time constant. One, you can say that time constant is the time in which the current reduces by 1 by E of the original value. 1 by E you will realize would come out to be I think 30, it will be 100 minus this, so 36.8%. Okay, so that is one way of defining that. Okay, so let's just confirm that value. So 1 by E, it will reduce by 1 by E. Yes, 36.8%. So there are two ways of defining time constant. So let's write here. Time constant is the time in which current drops to 36.8% of its initial value. So you realize the graph is very similar of the current in the circuit is very similar to the radioactive decay. There also you will see this kind of decay graph. So that is why you have this similar term for comparing. Instead of half-life, where everything drops by half, we talk about time constant wherein everything drops, the current drops by 1 by E. So after every time constant, the current would drop by 1 by E. And practically we assume that the steady state would start roughly after 5 time constants. So let's make a note of that also somewhere. Yeah. So let's add that here. Practically, steady state is assumed. Steady state is assumed after five time constants. So you will realize that in one time constant, the current is becoming E minus 1 over E. The charge is becoming this. In two time constants, what will it become? It will become 1 minus 1 by E square. So as the time constant is increasing, the charge would be approaching the maximum possible charge also, right? So after five time constants, what would be the charge? So you realize the charge after five time constants would be this 1 minus 1 over e to the power of 5. Okay, let's try and see what the value of that is. So if I calculate that, I will have that e to the power of 5, e to the power 5, and 1 over this. Okay, so this minus 1 into 100. So after this time, roughly the charge reaches the 99.3% of the maximum value. Okay, so that is where we assume that the capacitor is almost fully charged after five time constants. So this is nothing but this is Q equals 0.993 of capital Q. This is where you start assuming the steady state is almost achieved. Okay. I hope that is clear. So please let me know if you followed everything about the charging circuit, what time constant is, how the charge and the current in the circuit are changing, how the potential difference across the capacitor is changing. If you have any confusion regarding anything, then let me know and I will answer that. And if everything is clear, then I will move on to the discharging circuit. So now I hope, Rishabh, you are fine with the idea of time constant, what a time constant is, what steady state is. So you will see from this graph, that at roughly 5 time constant, we consider the capacitor to be fully charged. Why? Because it has already acquired more than 99% of the maximum charge. Okay. Alright. We will see how we will use this in circuits. You just need to remember this equation. This equation is very, very important. So just remember these equations. One, this equation, another, this equation. These two equations are what you need to remember for your problem solving. Okay. All right. Now let's move to discharging circuit. Okay. So once you have charged the capacitor, see, we always say that capacitor is a device which is used to store energy. So once I have charged the capacitor, what do I do now? Now I can use that stored energy while I am discharging the capacitor. While discharging, it can cause a current flow across a resistor. So in the discharging circuit, you will not have this battery. So you will not have this battery. You will simply have this. This is what a discharging circuit would look like. Okay, so if I can get rid of this. Yeah, this is what your discharging circuit would be. Okay, so the battery was made here by mistake. Okay, so this is what a discharging circuit is. You have a charged capacitor which you have connected across a resistor. Okay, and we are assuming that initially this capacitor was having some charge plus Q and minus Q. This is at t equals 0, and it has some plus Q and minus Q at t equals t. So what happens is that the moment I connect this capacitor across this resistor, you realize that there is a potential difference across these plates. So this is at a higher potential, this is at a lower potential. What that does is that it causes a current to flow in the circuit, right? So you will see this kind of a current flowing in the circuit. And as this current flows, essentially what is happening is that from this end, the positive charge is going and reaching here. So you realize the charge on both the plates would start to reduce. The positive charge on the positive plate would reduce, the negative charge on the negative plate would reduce, and hence the potential difference across the capacitor is decreasing constantly, which means the current in the circuit is also decreasing. However, till the time this capacitor gets discharged completely, it will keep on causing flow of current, and that flow of current will dissipate some power across this. So what we are using is that there will be power dissipated across this in the form of I square R. Where is that power coming from? That is the power that was stored in the capacitor. Okay, so please remember that. So let's assume that at t equals 0, the charges on the capacitor plates were plus capital Q and minus capital Q, and at some time t, the charges which are remaining are small plus q and small minus q. And at this instant, let's assume that the current in the circuit is I. Now what I can do is I can apply my KVL, and let's say I start from here. I start from here and I am trying to cross this capacitor from this side here to here. So when I'm crossing this from here to here, I'm crossing from the negative side to the positive side. And then when I'm crossing this resistor, I'm crossing this resistor in the direction of the current. So assume I am taking my loop like this. This is my KVL loop shown by orange. So applying KVL equations, let's see what we are getting. Applying KVL. So when I start from here, when I cross this, I'm getting plus Q over C. And here when I cross this, it will be minus IO times R, and this should be equal to 0. Okay. Now one thing. When this charge is flowing, it is getting here a plus dq charge. It is getting a plus dq charge. So the negative charge would have changed by. So if Q is the charge, you will see minus Q plus dq would be the net charge. Alright, after T plus dt. So at T plus dt, this would be the charge. At T, the charge was minus Q. So what is the change in charge? So change in charge, delta Q, would be minus times of dq. Okay. What is the change in charge of capacitor? The capacitor charge is reducing. It is reducing. Okay, so let's talk about the positive one maybe. At positive one, at t equals 0, the charge is plus q, and t plus dq, it is q minus dq, right? So on the positive plate, what is the change in the charge? It is minus dq. The charge is reducing. And you will know that dq would be equal to I times dt. So from here, what I will get is that, okay, so maybe we should have used some different symbol actually. You should have used some different symbol. Because this is causing a little bit of problem. So let's assume that it gets some dx amount of charge. So the charge would be minus dx. Now you can write dq is minus dx and dx is I dt. So from here I will get that I equals minus dq over dt. That is what I am trying to say. Why is there a negative sign here? The negative sign is here because this charge is getting reduced by a positive current. If the current is positive, then this charge is actually reducing. Okay, that is why you will have a minus sign here. Now all I need to do is equate this value and put it here. Now let's see what that will get us. That will get us Q by C equals, I will have minus dq over dt times R. So again from here what we will see is we will have minus or dq over q equals minus dt over rc. So let's just integrate this. This goes from capital Q to small q. This goes from t equals 0 to t. So what I will get is q ln q by q, or q by q, I can say, is simply e to the power of minus t over rc. So what I will realize is that q is equal to capital Q e to the power of minus t over rc. This is how the charge is decaying. Now this time, last time I got this kind of expression for current. Current was decaying. This time I have got this expression for the charge. The charge across the capacitor is decaying exponentially. Okay. If I wanted to have a equation for current, then also I will find that I would be equal to minus dq over dt. So let's see what that gives us. If I differentiate this, I will get I as q over rc, and the minus is taken care of by this minus into e to the power of minus t over rc. Okay, so you realize q over c was nothing but the initial potential difference across the capacitor. So v naught over r e times minus t over rc. So these are the two expressions that I am getting for charge and the capacitor and the current in the circuit. So this is the expression for charge as a function of time. So what is happening to the capacitor charge? It is decaying exponentially. What is happening to the current in the circuit? That is also decaying exponentially. Okay. So now let's take a look at these graphs. So this is what both the things are looking like. Okay. So the current is also reducing. The charge on the capacitor is also reducing. Okay. I think I will get some water, some more water, because I have very less water left. So give me 1 minute. You guys take a look at this graph. I'm feeling thirsty, so let me just quickly grab some water. Okay. Yes. So what we realize is here that again I can again talk about the time constant here. The time constant is again the time in which you realize the charge is getting reduced by 1 by e every time. After every time constant, I see that the charge has gotten reduced by 1 by e of its initial value. Okay. So as I said, now what I can see is that what is the amount of heat dissipated, or amount of energy dissipated across R. So what will that be? That will be nothing but integral of I square R dt. I know the power d e by dt or dq by dt, or however you want to say it. Let's write dh by dt is equal to I square times R. So obviously the total power generated, the total heat generated on would be I square R dt integral from 0 to infinity. Because what you realize is that here also the capacitor will get fully discharged at t equals infinity. So you can see from here q equals 0 at t equals infinity. So not only does it take infinite amount of time to charge capacitor, it will also take infinite amount of time to completely discharge a capacitor also. So again, what we will do here is we will not wait for the capacitor to get completely discharged. We will talk about a steady state which would happen after 5 time constants. And if I calculate this, you can try this. This is your homework, by the way. Try this integration. Homework. Okay. And guess how much it will come out to be? It will come out to be 1 by 2 q square over c. So try the integration. That is homework for you. You already know the expression for I. I have derived the expression for I. This is what I is. Now all you have to do is integrate I square r into dt from 0 to infinity. When you do that, you will realize you are getting your answer as q square by 2c. So what is happening is that the energy that is getting dissipated across the resistance is nothing but the energy that was stored in the capacitor in the first place. And let's see what else I can notice from here. What is happening at t equals 0? At t equals 0, the current is V naught over R. Okay, and at t equals infinity, the current is 0. So at t equals 0 in a discharging circuit, so a capacitor in a discharging circuit is essentially behaving like a battery, right? Wherein if the instantaneous charge in the capacitor is Q, then the potential difference across it is Q by C. So it is at every instant behaving as a battery of potential EMF Q by C, right? So capacitor in a discharging circuit is behaving as a battery of decaying EMF. So it is behaving as a battery for which the EMF is getting decayed with respect to time. Right? At t equals 0, if it was charged initially to V volts, then at t equals 0, it will behave as a battery of V volt. And after time constant, after one time constant, you will realize that the charge would have become 1 by E, and hence the potential difference across it would have also become 1 by E. So it is behaving as a battery which started with an EMF of V naught, which was the voltage to which you had charged the capacitor, and after every time t, what is happening is that its EMF is getting reduced by 1 by E, 1 by E, 1 by E. It is continuously falling down. Okay, as you can see from these graphs. This is the capacitor voltage. It is continuously falling down. After every time constant, it becomes roughly this. Okay, so yeah, it becomes roughly 36.8% of the initial. So after every time constant, this is happening. Okay, and the current, you will also realize, current is also decaying like this. Current is also reducing by the same percentage after every time constant, and eventually it will become 0. And in this entire discharging, the entire energy stored across the capacitor is getting dissipated across the resistor. So in this circuit, the entire energy stored in the capacitor is getting dissipated across the resistance. So that is why we wanted to use capacitors in the first place. I told you capacitors are nothing but sources of energy. We will store energy here, and then whenever I need, I will use this energy. I will discharge a capacitor across a resistor, and this is how the discharging would happen. The discharging would not happen instantaneously. The discharging would take infinite time, and in all this discharging, the capacitor behaves as a battery whose EMF is continuously decreasing. So the current from the circuit would be continuously decreasing. It would take infinite amount of time for the capacitor to get fully discharged. However, in this infinite amount of time, it would have dissipated the entire energy that was stored in it across the resistors. It would have transferred the energy stored to the load resistance, which would have dissipated or consumed this power. Okay. So again, a time constant here also we discussed that time constant T is nothing but RC. So that is tau actually. We use the symbol tau for time constant. And again, time constant tau is RC. Again, why? Because as I said, the total time taken for the charge capacitor to get discharged is infinite, right? So if the total time for getting discharged is infinite, there is no point in comparing two circuits by looking at the total time required to discharge them. So which one is getting discharged faster? Which one is transferring the energy faster? So to compare that, again we talk about time constants, and you realize the value of time constant is same while charging and discharging. So that is another interesting thing. Okay, so please remember all these. So let's write why do we need the time constant? Because since the total time for discharging is also infinite. For studying or comparing various RC circuits, we use tau. Alright, so whenever we are analyzing or comparing different RC circuits of discharging, we again talk about tau. Tau is the time, it is the time in which, now here all the parameters will drop, whether it is the charge on the capacitor, whether it is the current, whether it is the potential difference across the capacitor. So it is the time in which the charge, the current and the potential difference across the capacitor drop by a factor of 1 by E. So 1 by E we already said was nothing but 36.8% of the original value, or 36.8% of the original value. So again, as I said, for studying these circuits, instead of using term like half-life, we use a term like time constant. It is a very similar concept as that of half-life. So after every half-life, I told you when you start with, let's say, X number of radioactive molecules, after half-life you would be left with X by 2. After another half-life, this X by 2 would become half. After another half-life, this would become half. Similarly here, we are using the concept of time constant. We are just using a different term, where in mathematical equations I can see every time everything is falling by 1 by E. So okay, so after one time constant, if I started with a charge capital Q, the charge would become 36.8% of capital Q, and after another time constant it will become 36.8% of this initial charge. So it would be 0.368 square times Q, and so on. Now these time constants help us compare these circuits. Why? Because practically again I would assume that the discharging is complete after 5 time constants. So again, practically discharging is assumed to be complete after 5 taus. Okay, so you realize again here also everything would keep on changing until the steady state is reached, and this is what you will call steady state. Again, this would be called the final steady state of discharging. Why? Because now things have stopped changing. Before this, everything will keep on changing. Your voltage, your current, your charge in the capacitor will keep on changing. After 5 time constants, everything becomes zero, and that is what you can say is the steady state of the circuit. So this is what is there about discharging and charging of the RC circuits. So please go through this and let me know if there is any confusion. All you need to do is remember this equation, very important. So please make sure you remember this. Important. This is very important. These two equations are important. Okay, so make sure you remember these. Then of course you have the discharging equation. This equation also. For time constant, you should remember this. That this is how you define a time constant, and in one time constant, you realize the charge becomes this. The charge after one time constant becomes like this, and the current after one time constant becomes like this. So the idea of time constant should be clear, and the value of time constant you should know immediately is equal to R times C. Okay. Dimensionally also you will see R times C has the dimensions of time. Similarly, this equation for discharging is important. This equation for discharging is important. So these equations should also be remembered. And for these circuits also, okay, these circuits also you will remember that tau is RC only. And again here, everything after every time constant is followed by a factor of 1 by E. Okay. So one more thing, one last thing that I wanted to discuss was that if you are talking about the charging circuit, you will realize that after steady state at t equals infinity, what is the energy stored in the capacitor? It would be half CV square. What would be the work done by the battery? It would be CV, by the way. So you will realize half the energy would have gotten dissipated across the resistors. So just let's make a quick note of this. Okay, at t equals infinity, the capacitor stores energy equal to half C E square. Okay, and also the energy dissipated across the resistance in this time would be equal to half CE square only, and work done by battery would be equal to CE square. So you should remember all these. That in the charging also, you realize that once the capacitor gets fully charged, the complete charge on the capacitor would be C times E. So the C times E charge has flown through the battery, in which the battery would have done a work of CE square. Out of this, half gets stored in the capacitor and half gets dissipated across the resistor. So that is an unwanted result, of course. When you wanted to store half CV square amount of energy in the capacitor, you had to dissipate half CV square amount of energy across the resistor also. You can check that by integrating this expression of I square R, by the way. So here I think we had an expression for I. Yes. You can integrate I square R from 0 to infinity and you will get the answer as half CE square. Okay. Hi Roshan, how are you? I am good. Okay, so this is all you needed to know about the charging and discharging of capacitors. Okay. Next, So now, right now, we were only talking about the simple RC circuits which had only one battery, one resistor, and one capacitor. What happens when we are encountered with more complicated circuits? Then again, what you will do is, in general, the most general approach would be using your KCL and KVL. Even if you have no matter how complex circuits they give you can always use your KVL and KCS. There are some other ways also with which you can reduce that effort. So what you can do is, whenever you have a circuit, you can convert that into a circuit containing a single capacitor and a single resistor, and then use the equations which you have already derived for this kind of circuit. So how do you do that? If you have various resistances, find the R equivalent. You find the R equivalent, and if you have various capacitors, you find C equivalent. And once you have found the R equivalent and C equivalent, you will realize that the time constant for any circuit would be R equivalent times C equivalent. That is the idea also that you can use to analyze these circuits having multiple resistors and multiple capacitors. Okay, you convert them into a circuit having one single capacitor or one single resistor. Okay, but that will not be always possible. Okay, that will not be always possible. So sometimes you will have to just apply your KCL and KVL only. Okay, so let's take an example of this question. So this is a question that has been asked in JEE Advanced. Okay, so let's see. It says a RC circuit is shown below. Now initially the capacitor is uncharged and the switch is closed. Now after a long time the switch is open again. Find the new time constants. Find the time constants both during both the parts and show the variation of current with time across both the R's. Okay. Yeah, this must be show, not shown. So let's see what is happening. Initially the switch is closed. Initially the capacitor is uncharged and the switch is closed. So please pay attention to the initial conditions. This is what your initial condition is. Now it says after a long time. So what does that mean, after a long time? Implies after steady state was achieved. So whenever it says after a long time, you will assume that the steady state was achieved. Okay, so how do we find the charging constant and discharging constant? So initially when you put the switch off, so initially you will realize there would be some current I, some I1 would go here, some I2 would go here. Okay, and this is where the charging would have happened, right? And later, when you open that switch, once this has gotten charged, then discharging would happen. So you have to find the time constants for the charging circuits and the discharging circuits. So immediately, you should be able to do that immediately. Try that immediately and let me know. You have 1 minute to give me the answers for both. So what will be the charging time constant? Just think about it. Quickly, quickly. Is anyone trying this? डायरेक्ट नहीं होगा ये सर, डायरेक्ट हो जाएगा, डायरेक्ट हो जाएगा, क्यों नहीं होगा? यस, सो व्हाट इज द आंसर? डायरेक्ट होगा तभी तो बोल रहा हूँ. You can do it directly. That is why I said you should be able to answer, give the answer immediately. Just look at the circuit more carefully. Just look at the circuit more carefully. See, most of the current electricity circuits that you find difficult to solve, no, that won't be the case. Let me tell you. While charging, I can just redraw the circuit like this, right? So mostly this circuit, see all the circuits that you will see, mostly they are misdirections. They have been drawn in such a way to confuse you, and you get confused. So now you realize what is happening in the charging. In the charging, you have this loop. You realize if even if I remove this, do you think there will be any difference? Do you think there will be any difference whether I have R2 connected or not? Will there be any difference in the charging of this capacitor? Even if I remove R2 now, it is only applied parallel to that, right? So it is not interfering with the current that is flowing with the circuit. You realize that even if I had this kind of circuit, only this, and this, they all these currents would be perfectly identical, because in both these cases you realize that the potential difference across this combination is E, across this combination is E. The presence of this charge, this resistor does not change anything in the charging circuit. So you have to focus on the charging circuit. What is the charging circuit? The charging circuit is only this. Okay, no matter how it has been drawn, the charging circuit is this only. The rest is additional circuit that has been attached to it. So when you see the charging circuit, now you have no issue. Now you know the time constant. So time constant tau charging would be simply R1 times C. Okay. Now let's take a look at the discharging circuit. At discharging, you realize this was disconnected. When this was disconnected, when this switch was open, then what is happening? Then the current would be flowing across this, like this. Okay, if when the switch is open, so when switch is open, let's see how the current flows. You can remove the battery now, and you have this, and you have this, and you have this. So this would have acquired some plus Q charge, this would have acquired some minus Q charge, you have R1, you have R2, and the currents would now start flowing in this. So this is your discharging circuit. So in the discharging circuit, you realize that R1 and R2 are connected in series with each other. So you can convert them into a single resistance of R1 plus R2. So tau of discharging will simply become tau discharging would be R1 plus R2 times C. That's it. Yes, Roshan, tell me. No, not R1C by R2. Why R1C by R2? R1 plus R2C. Yes, so this is what you need to do. Whenever you are given a circuit, you identify the charging circuit, you identify the discharging circuit. Where is the charging current flowing? Where is the discharging current flowing? So the moment you have identified that, now you find the net resistance and the net capacitance. And the time constants would be this. Now you realize writing the equations for this entire circuit would also be easy. Now let's imagine, now that I have this time constant, what does that help me with? So when I have this time constant, so while charging, I can say, so when this is connected like this, I can immediately write all the equations. While charging, Let's see, what do we have? I have I1 and I1 has a time constant of that. Now all I need to do is I need to remember the equation of I1. What was the equation of I1? I1 was, I1 would have been I1 max into e to the power minus t over tau. Okay. Now what is I1 max? I1 max would be the I1 value of I1 at t equals 0. Right? I1 max equals I1 at t equals 0. So if I can find that, I can find the expression for I1. I already know the time constant. Now that is very easy to see. I told you that a fully uncharged capacitor behaves as a resistorless wire. So I can say at t equals 0, C equals resistorless wire. Right, so if I replace this capacitor with a resistorless wire, then I know that I1, how much will the I1 value be? I1 would be epsilon over R1. I hope everybody agrees on this. That if you realize the potential difference across these would be E, the potential difference across these 2 points would be epsilon, and you have only R2. So R2, okay, so I took the values of R1 and R2 different, I think. Let's keep them consistent. Let's call this only everything related to 1 as 1 and everything related to 2 as 2. So let's write this, 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 this. Okay, then here also the tau would have R2 by R2C. Okay, and here so I think I chose the wrong subscripts. Let me just correct that quickly. Okay. Now what you will realize is very, very interesting. Very, very interesting. Now I can completely write the equation for I2. While charging, I2 would be epsilon over R2 e to the power of minus t over R2C. Correct? How about I1? Also. Now I1 would be normally constant. Why? If you look at here, the current in this, again, since these are parallel, is unaffected by the other circuit, right? Is unaffected by the other circuit. So I can say that I1 would be nothing but a constant value of epsilon over R1. So I1 would be epsilon over R1, which it would be a constant value. It will not change with respect to time. Now, if I wanted to write about I through the battery, from KCL I could have said I would be equal to I1 plus I2. So current through the battery, therefore current through battery becomes I equals epsilon by R1 plus epsilon by R2 times e to the power of minus t over R2C. So you realize you have expressions for everything. Whatever may be asked of you, you may immediately get all that with the help of everything that you have learned already. Okay, you wrote I2 in terms of time, you knew I1 would be constant, you could find the current through the battery, which is this. So now you realize for charging, you could have told us anything. You could have told anything. What would be the steady state current? In steady state, you will realize I2 would drop to 0. There will be only I1, which would be E by epsilon by R1. Okay. Similarly, at any time, what would be the charge on the capacitor? That also you can say now. So what would be the charge on the capacitor? What is the final charge on the capacitor? Final charge on the capacitor would be CE. So you could have written the equation for that also. Q would be CE times 1 minus e to the power of minus t over R2C. That's it. The moment you know the value of time constant, you can write all the expressions. Okay, so please remember that is the importance of finding the time constants of different circuits. The moment you find the time constant, you can write all the values for all different currents or all different charges or the different potential differences. Yes, Osho. So I was just finishing up my discussion only. So please go over the solution and try and understand why do we need to calculate the time constants and what all can we tell with the help of time constants. So I did have a couple of more questions for practice, which I think I will take up in the next class. Okay. So this is where I would like to wrap it up for today, and I will discuss the rest of the stuff on Tuesday. So make sure you've gone through this video once very thoroughly, and also do not miss the video on Tuesday. So before I leave you, let me remind you that you should be getting your Plus subscriptions if you haven't gotten them already, and this is how you do it. Go to the Plus section in your app, select your goal as IIT JEE and click on Get Subscription. Okay, and for those of you following us on the JEE English channel should connect with us on the Telegram app using this link. If you like today's video, press the like button and share it with as many people as you can. As you know, this is a free content that Unacademy is providing to all the students who can't afford the subscription. So make sure more and more students are benefiting out of this. Okay, yes, bye Osho. Don't forget to press the bell icon, and the PDF would be available very soon. Now, before I leave you, let me remind you, this is my code RDLive. If you should be getting your Unacademy subscriptions, if you haven't gotten them already, and you can use this code and get a 10% off. So as I keep telling you, the JEE exam is one of the most competitive exams ever that you will face. To crack this with a top rank, you will need all the help that you can get. So get that help with the help of your Unacademy subscription. Get that edge over your competitors, and that is it. That is it from my side for today. I will see you next on Tuesday. Till then, you guys keep studying, keep practicing, and take care. Bye-bye.